So today's topic is what's called logistic regression, which is a really important idea for a couple of reasons, not the least of which is it's going to introduce a very important cost function called the cross-entropy cost function, which we'll definitely be using again after we talk about linear methods. So logistic regression is kind of weird because it's like, okay, well, we talked about regression being a way to forecast a continuous number, but when people talk about logistic regression, often they're talking about doing a classification problem where there actually are labels. And so really today, what I'm talking about is binary classification via what's called logistic regression. And so previously on machine learning, we had basically, binary classification via a linear discriminant. And the setup was basically that I take my input features x, I weight them by some weight vector w, maybe I add a bias, or maybe if I want to include the w0 in here, I just kind of have a row of ones in my x vector. And then basically I decide on, if this is greater than 0, then I choose class 1, and if it's otherwise, I choose class 2, right? And so last time we kind of went through the idea of that using least squares as an idea for solving this problem as a classification problem is not that great due to the sensitivity of least squares to outliers. So then we talked about this idea called Fisher's discriminant, which had the premise of trying to minimize the within class scatter while maximizing the between class scatter, and showed how that could do a good job of separating distributions. And I'm going to definitely ask you to demonstrate that on the upcoming homework. And so today we're going to talk about this other option called logistic regression, okay? And so the difference here is that we're going to introduce some nonlinearity. And as we're going to see, especially when we start getting into neural networks, having some sort of nonlinear element to my decision makes a huge difference in the performance of these algorithms, right? So, the idea is that logistic regression introduces a nonlinearity. So my model is going to look like some function of W transpose X, where this here is some nonlinear function. And what that means is that now my decision is no longer going to be linear in the weights. It's going to be nonlinear in the weights. So how should I choose what this function should be? Okay. Well, let's go back to Bayesian decision theory, which we talked about a few weeks ago, right? So what would be a good choice for this f? So let's go back to Bayesian decision theory. The motivation there was that we had classes and priors, and we're trying to choose the class that had the highest posterior probability, right? So we're looking at the posterior probability of class 1 given the data, which we modeled using Bayes' rule as the class conditional PDF of X given the data times the prior over, this is what you'd call the evidence, right? To expand this out, this is like saying I basically, in a binary classification system, have two classes. And the denominator here, I can kind of expand out when I've only got two classes, because there are only two possible states of nature. Either X is in class 1 or it's in class 2. Okay? And so now what I'm going to do is I'm going to define a new number related to all these things here. So let's define A as the log. And again, just a reminder, whenever I say log in this class, I mean natural log, right? Log base E. And I'm going to look at that as basically this ratio. And actually, you can see that this ratio fundamentally is also like the ratio of the posteriors. So this number is called the log odds sometimes. And so now what I want to do is I want to write the posterior probability in terms of this A. Okay, so with a little bit of manipulation, I can show that, we can show that the thing at the top of the paper is related to A by this much simpler equation. And I think that you could probably kind of convince yourself why that's true just by kind of like working it out. Because e to this thing, that gets rid of the log, and then I've got, the ratios of these other numbers come into play. And I'm going to call this function sigma of A. Okay, and so this sigma function, oh, is that a question?
Yeah, how do you take out the POC probability of C1 and probability of C2 then?
So where did all that stuff go? Well, that's all kind of embedded inside this A, right? So if I want to do a quick back of the envelope calculation, let's just show why this is true, right? This is like saying I have, 1 over 1 plus e to the minus A is just, looking at this, it's like taking e to the, minus log, right? So what I'm going to get is this ratio, right? Dot, dot, dot. Oh, sorry.
I'm like above, like on the previous page. So like, how did you get from that with the POC1 and POC2? How did you take those out?
How did I take them out?
Like how did they? Oh wait, I'm sorry.
You're okay. So the ratio of these things, the p of x drops out. If that's kind of what you're asking, right?
Yeah, right.
Okay. Good. All right. So let's move on. So it's like saying that if I let me write this again in a more clean way. So basically, we can show that this is true. I'm going to define this as this function sigma of A. Okay. Now this is a key idea because A, right? A is the ratio of, basically these two numbers and taking the log, right? So if this is a really big number, right, that number could be infinity before I take the log, and after I take the log, it's still infinity, right? If this is a super small number, then that number could go all the way to minus infinity. So this A could range from, minus infinity to infinity. So if I make a plot of A, I could basically have, minus infinity to plus infinity, right? But when I take the 1 over 1 plus e to the minus a, what does that function look like, right? Well, when a is really big, I basically have this e to the minus a turns into 0, right? So I have 1 up at this end. So basically I have a mark over here. And then when I'm at minus infinity, it's like saying I have 1 over some huge number, infinity, which is 0, right? So over here, it's 0 way at this end. And so my function looks like kind of something that smoothly goes like this. And so when a is equal to 0 right in the middle, I have 1 plus 1 in the denominator, so I have 1/2. Okay. So this function is called the sigmoid function. And sometimes, just to be really clear, it's called the logistic sigmoid function. And it's called sigmoid because it looks kind of like an S. S for sigmoid. And so this is an idea of saying it maps any number into the range of 0 to 1. Why is that important? It's important because at some point we're going to think about interpreting this like a probability, right? So probabilities we know have to be between 0 and 1. So this is like saying that I basically take the ratio of the posteriors, which could be anything, and then I map it into this nice 0 to 1 range. And so this idea of mashing a number into the 0, 1 range via this equation will become important again in future lectures, okay? And so how would I do how would I make a classification algorithm based on this idea? Well, the natural thing to do would be to say, okay, well, when the ratio of the posteriors, when the sigma is greater than a half, I choose, class 1. Otherwise, I choose class 2. So let me just write that down. So it's like saying we get a binary classification algorithm by choosing, if sigma is greater than 0.5, I choose class 1. Otherwise, I choose class 2. Which is kind of like the equivalent of saying, if this function is greater than 0, do this. Otherwise, do that, right? So I can kind of think about it in terms of A, or I can think about it in terms of sigma. And so here, this is all just kind of like, again, rewriting Bayesian decision theory in a slightly different way with this sigma instead of with the original, actual values for the probabilities. And more generally, what if I had more than 2 classes, right? So for K classes, right, my posterior is again, via Bayes' rule, the class conditional probability times the prior over the sum of all of the ways that can happen. This is basically like the evidence in the denominator. And I can again rewrite this in terms of like A's and sigmas by saying this is like, e to the AK over the sum of e to the AJ, where the AK is again like the log of this. So all I'm doing is I'm just kind of like giving these things a new name. And then I would just choose the class that has the biggest posterior. That's what we usually do in decision theory, right? And so again, this is a kind of an important idea that these A's could be an arbitrary, could be close to plus infinity, close to minus infinity, right? But this function will map that vector of A's into a vector that sums to 1. So let me write that down very clearly. So this function that takes the vector of A values and maps it into, this vector, this is called the softmax function. And we'll see this again for sure. The reason that we like to do this is it takes a set of arbitrary numbers and maps it into a vector that adds up to 1 and has numbers that can be interpreted like probabilities. So this is important since it takes any vector and maps it to a vector that sums to 1, elements that are in this range 0 to 1. And the idea is that we can interpret this as a probability mass function, right? As a probability vector. Okay. So this is kind of actually going a little bit backwards to Bayesian decision theory. How does this come back to this idea of drawing a straight line that separates 2 classes, right? That's what we're really here to talk about, is linear classification, right? So how is this related? So let me stop for a second. Questions or comments about what I've said so far? Yes?
Could you go back into the I think it's good to record that actually. Thanks. So I'm confused on how kind of like that equation then shows you how shows you kind of like what class do we say, because it isn't Doesn't A have the probability of C given X?
Right, so A is basically this. A is the ratio of these posterior probabilities, right? So it is that if these things are equal, I flip a coin. And then in this case, this ratio is 1 and A is equal to 0, right? If this posterior probability is bigger, then I want to choose it, right? Which means that this number is going to be greater than 1, and this number is going to be positive. And kind of, that means that sigma is going to be greater than a half, right? If these numbers are, if this posterior down here is bigger, then this number is less than 1. I have a negative log, right? A is less than 0, and I'm on this side, right?
So is that, but that whole equation, the sigma, that's equal to the A plus posterior probability of sigma?
So yeah, so this whole thing, this is a different way of writing the posterior probability, right? And it kind of makes sense that I want to choose whichever posterior probability is higher. These two numbers have to add up to 1, right? So if the posterior of one of them is bigger than a half, that's the one that I should choose, right? That make sense? Okay. And in general, with K classes, I want to choose, I've got a vector of posteriors that adds up to 1, and I want to choose whichever one is bigger, right? Okay. So how does this get back to linear classification, right? So, how is this related? To linear classification. Well, the relationship, right, our rule is, if our rule is choosing sigma greater than 0.5, going to, class 1, that's the same thing, just rewriting 1 plus e to the minus alpha is greater than 0.5, which is the same as saying alpha is greater than 0, or a, I'm sorry, not alpha, a, right? And so the thing is that if this a, if a is a linear function of the data, W transpose X plus some constant, then this whole thing is a linear classifier. Gives us a linear boundary in feature space, right? So that's kind of like the connection, right? It's like saying if I model A as linear, then that corresponds to, in the original data space, this rule splitting things in half by a hyperplane, right? And we should already kind of remember this from Bayesian decision theory on Gaussian distributions, right? So basically, recall that if the class conditional densities are Gaussian, we already found. So Gaussian, let me say, with the same sigma, the same covariance matrix. Then we already found that this discriminant function is linear with the weights that depend on the mu and the sigma. So there should be something kind of in the back of your head that's like, okay, I kind of remember that if I had, a cloud of points over here and a cloud of points over here, that the Bayesian boundary is like the, a straight line that separates them, right? Now, why am I doing something, why is this any better than just like modeling everything as a Gaussian and finding the Gaussian, finding the Bayesian decision rule according to this bunch of Gaussians? Well, if we were going to go at this problem via density estimation, then if I'm in some high dimensional space, what I have to do would be to model each of my class conditional distributions with a Gaussian, and the higher the dimension, the more parameters I have, right? So first I'd have to fit the Gaussian with all the parameters, and then I'd have to find the classification boundary, whereas with logistic regression, I'm kind of just specifying that I'm going to try to find these numbers, and there's only kind of a smaller set of parameters. Let me write that down a little bit. So, if we were to explicitly model the distributions as Gaussian, then I would need a lot of parameters, right? We'd need, 2m vectors for the means plus all these numbers for the covariances, right? Which is a lot. Instead of estimating all those parameters and coming down to find these m numbers, instead, logistic regression just uses m parameters directly, which are the weights. So, that's a big advantage of this idea, is that instead of fitting all these high number of parameters and then finding, the m numbers that define the decision boundary, instead I just talk about the decision boundary directly and optimize over that, right? So I'm going to do some more, interpretation of what's going on here. But at this point, it's a good point to say, like, okay, so, linear regression, or I'm sorry, there are a bunch of ways of finding this hyperplane, this straight line that divides the sets of points, right? I could use Fisher's discriminant, or I could use this method I'm telling you about today, logistic regression, or I could use what's called a support vector machine. We'll talk about that on Monday. So these are all just basically different ways of getting at a good boundary, and where good is something that is defined by the method, right? So in a way, there's no right answer. It's just a question about, like, what is the cost function that I'm going to optimize, right? So Fisher's cost function we talked about last time had to do with this idea of variance between clusters, right? The idea we're going to use here uses a totally different cost function. That's called binary cross entropy, which we're going to introduce in like 5 minutes, right? So let me just kind of write that down. We have a bunch of options. We have Fisher's discriminant. We have logistic regression. We have support vector machines, SVMs, which you don't know about yet, but you will learn about on Monday. Basically, these are all ways to fit a decision boundary and the difference is the cost function. That we minimize. And there's really no absolute best answer. A lot of it is heuristic, right? So if you're trying to do linear classification, what you may do is you'll first try logistic regression, and then you'll try an SVM, and you'll see whichever one gives you the lowest classification error for your data, right? There are some underlying assumptions. So for example, the algorithm I talked about last time, Fisher's discriminant, is really implicitly modeling the distributions as Gaussian, right? Which means that when your classes really don't look Gaussian at all, then the kind of assumptions of Fisher's are not really satisfied. Whereas there are no such assumptions with logistic regression. You're just fitting this thing, right? But the more important thing about this logistic regression that I want to really get at is the cost function, right? So last time I kind of mentioned that like trying to solve this as a regression problem where I'm trying to fit like outputs to binary vectors doesn't make a lot of sense because the errors in the observations that come from a least squares assumption are not like Gaussian distributed, right? What would make more sense to use as a cost function, right? So, our model for the whole classification problem is that we have binary labeled data where I have, inputs and outputs. And today, I'm just going to switch my output so that it's either 0 or 1, right? So I guess in previous, lectures, I've kind of said class 1, class 2. Today, I want to just have a label of 0 or 1, right? Nothing has really changed, right? And then the key idea is that we're going to interpret the function y equals sigma of W transpose X as a probability. So again, in binary classification, that's like saying that the probability that the class label is 1, given the data and the weights, is this number. And the probability that the class label is 0, given the data and the weights, is 1 minus this number. So this is like a posterior PMF over the two possible states of nature. Either my label is 0 or it's 1. These two numbers have to add up to 1. Okay. And so there is a more compact way of writing this, which is a little bit tricky, but if you think about it, this is like saying that the probability of t given x and w is equal to this. So I'm raising this to the t power. This is not transpose, it's now, why is that true? Well, let's think about it. So, this is just a fancy restatement of these two equations put together, right? So when t equals 0, then this number to the 0 power goes away, and I have the bottom equation, right? When t equals 1, then this exponent is 0, and I got this, right? So this is just a way of kind of encapsulating for the two possibilities what can happen, because only one of these terms can be non-zero or not equal to 1, right? Sorry, only one of these terms is not equal to 1. And so now the idea is that if I have a whole bunch of data, right? So now let's suppose I have not just one sample, but I've got n samples, right? Because usually we have lots of samples in our classification problem. So for all n of the data samples, and again, we're assuming that these data samples are all IID, right, coming from the same distribution. Then the probability of all of the class labels given a set of weights is the product of all these things. And now I'm going to just kind of like remember, I'm just going to kind of abbreviate this. This thing in here is the same as y, right? This is like saying I have the model prediction to the TI power just a reminder, this is like saying that yi is sigma of W transpose xi. And this is some continuous number between 0 and 1. So I'm slowly kind of building up this, more and more complicated looking probability. And what I want to do is I want to maximize this probability, right? I want to maximize the probability of the observations given the model, right? And so I would use my usual trick, right? So we want to maximize this. And then again, we apply, the usual trick of taking the log to make our life easier. So if I take the log of this thing, this is basically the same thing as, minimizing this cost function. A lot of times we like to phrase things like minimizing a cost function. So we're going to minimize the log of this probability, which now, taking the log of this thing, is pretty easy to do, right? That's like saying that now I have the sum over all of my data points, and I'm going to take this negative sign outside. I have ti log yi plus 1 minus ti log 1 minus yi. Okay, so this is the result that I really wanted to get to and talk about. This is called the binary cross entropy loss. So this is called the binary cross entropy loss, or BCE loss. And again, what is the interpretation of this? And I think that's good to try to develop some intuition for what's going on here, right? So kind of what I'm saying is that, these TIs, right, which are the, observed class labels, are binary, right? So this thing is binary, right? This thing is not binary. This is continuous, right? But kind of what I want to do is I want to make this as small as possible. So this is like saying that, if ti equals 1, then what I want is I want to make this number really big. So the negative of this is really small, right? So that means that we want log yi to be big, which is like saying I want yi to be big, i.e. close to 1. If ti equals 0, then I'm in this world. This term drops out and I'm over here. That means that I want, log 1 minus yi to be big, which means that I want yi to be small, close to 0. So kind of the way I think about this is that I have a set of binary vectors, or I have a set of binary numbers, and I'm trying to drive the outputs of my model to be as close to those binary numbers as possible, right? So, if I'm trying to hit the binary classification of 1, right, maybe the yi that I get is like 0.95. That means that I'm pretty close to being sure I'm in class 1, right? And so I'm trying to do, and this will make a little more sense when we talk about looking at this with more than 2 classes, but that's the idea, is I'm trying to basically take a number that I know is binary and try to drive some continuous number to be as close to that binary number as possible, right? So that's, that's the key idea. That's what we're going to minimize, and minimizing this thing is basically what's called logistic regression and classification, okay? Now I know this is a lot, so it may take a little bit of more going back and studying and looking at it again for it to sink in. But let me just pause. Questions and impressions so far? Yes?
Can we go back to the I'm a bit confused how you extended it for the multi-class one from a binary to multi.
Oh, so I'm gonna do that a little bit more clearly in a minute, right? So yes, we'll talk about the multi-class part after I talk about the binary part. Yes, and in a way, I think actually the multi-class one is, well, okay. So I mean, actually, why don't I just do that now since you asked? So, what about multi-class? Multi-class classification, right? So remember, our setup was that our posterior probability, which we're going to call yk, is equal to this softmax function. This number, again, is between 0 and 1. And this ak is a linear function of x, right? So the idea is that, if we have more than two classes, what we need to do is we need to learn a weight vector for each class, okay? That is that we learn an m-dimensional weight vector for each class. And the training has a different form, right? So the training has the form that each of the TIs is a what's called one-hot vector. Right? So for example, so we have TI as a one-hot vector. That's like saying that if I'm trying to target class 3, like this is my T, then I'm trying to drive my Y vector to look like this. But my Y vector, I'm thinking about like a vector of probabilities, right? So for example, maybe my Y vector looks like this, right? So I'm trying to push the Y vector, which is a bunch of continuous numbers, it looks like a set of probabilities that add up to 1, over to this binary vector, right? So I need to try to make these two things as similar as possible, right? And that's actually even easier to write because, if I'm looking at this, basically only one of these vectors is not, or only one of these entries is not 0 on the T side, right? So the general loss, the cross entropy loss, it's not binary anymore because I have more than two classes. Now I'm trying to solve a problem that involves, k m-dimensional vectors. Again, that comes from trying to minimize the log likelihood or the negative log likelihood of the observations given the weights. I can write that like the following. I sum over all my training data and over all of my classes. So again, this is over all my data. This is over all my classes. The target value, which is again either 0 or 1, times the log of the observation value. And remember that only one of these is not 0, right? So there's really only one term in the sum for each training sample, right? It's the one for which TIK is equal to 1, right? And for those guys, I want to drive the log YK, the number that's in this position of the vector, to be as big as possible. And I let everything else be as close to 0 as possible, right? So this is what I would do in the more general K-class case, right? In the 2-class case, I don't have to learn 2 WKs because I'm really only looking at one decision boundary, right? Here, this is the way of kind of generalizing it to K. Does that kind of, yeah. This, again, this requires some thinking, right? So, let me just write down kind of what I tried to say as intuition is that, for the, T K that equals 1, we want to drive the model output yk to be also close to 1. And the error is basically how far away I am from 1 for all my data samples for the classes that are true, right? So again, let me try to say that one more time. So the way to think about the error function is like saying, okay, I'm going to push my data through my model with some given w's, and I'm going to get some outputs y. Those y's are interpreted as class probabilities, right? And so all this is saying is that for the class that is true, I want the sum of those probabilities to be as big as possible, right? Which I think hopefully makes some intuitive sense. I don't really care what the values of the yk are for things that should be 0. I just want them to be small, right? They don't even come into the cost function because as long as I maximize the one that's true, everything else will be fine, right? So that's the multi-class version. And so you will see, and we will see again, this idea of how should I try to design a cost function that relates classification type data. This is the right way to do it, right? Because I have something where I'm building from the very beginning a cost function that knows that my targets are supposed to be binary vectors, and I'm kind of thinking about trying to drive my model output, which is kind of what I get by putting a softmax function at the very end of my classifier. I want this thing to be as close to this thing as possible, okay? Okay, again, definitely requires you to do a little bit more thinking and convincing offline. But I think also once we start to actually do this operationally, right? So I think that, not so much in homework 3, but homework 4 will be like the neural network homework, right? And when you do that homework and you start to see the outputs of the network giving you these Ys and thinking about interpreting those as class labels, then I think that things will kind of start to gel a little bit more firmly once you actually are doing it with real data, okay? And I'm sure once you start to use this on your project, right? When you're thinking about if I have a classification problem and I want to use, softmax at the end of my, network, then you'll understand why you're doing it, right? Okay, so how do I actually solve this problem, right? I mean, so now what I've done is I've posed the cost function, right? How do I actually find the minimum W, right? So unfortunately, life is not as easy as it was before, right? So here, let's go back to the binary case for a second. So here's my binary case. Suppose I've just got 2 classes. I'm trying to find the best W's, right? So the problem is that this Y here, there's some nonlinearity going on, right? So the Y includes this, this sigma, right? So this sigma here is what makes everything complicated because no longer, when I take the derivative, is it like this simple linear system? Because now I've got this weird e to the whatever function inside my cost function. So, minimizing the cost function unfortunately can't be done in closed form. Closed form basically means that I can just write the answer down, right? So for example, last time for Fisher's discriminant, I could just write down what was the best W. It was this matrix inverse times this other vector, right? Same thing for least squares problems. I could write the answer down. It's phi transpose, phi inverse, whatever, right? Here, I don't have the ability to do that. And the problem is, the issue is the nonlinearity, this sigma function, right? That's the problem. And so what can I do? Well, what I can do is what I talked about a couple of lectures ago, which is gradient descent, right? So when I have a cost function that I can't optimize directly, I can try to solve it numerically, right? So we need to use a numerical algorithm like gradient descent. And it turns out that it's not that hard to compute the gradient, right? So let me just say that, it turns out the gradient is pretty easy. I can actually write it down. It's the sum over all the data points of this. And actually, looking at this, again, remember, this thing is this nonlinear function of W transpose times xi, right? So this is basically saying, every point, it's kind of like a weighted sum of the points, right? This is like saying that, I'm basically adding all the points together, and the weight on each point is how far off I am from the correct classification, right? Because I'm trying to drive these guys to be the same number, right? This is a binary number. This is a non-binary number. But the idea is that I want this thing to be small. So the interpretation here is that a weighted sum of the x values where each point contributes proportionally to the error in prediction. Which is this difference between what I have and what I want. So that's kind of a nice interpretation. And it turns out that, when I can write the gradient down like that, then it's pretty easy to implement the gradient descent. The other nice thing that you can show is that this cost function is convex, right? So also, the cost function is convex, which we talked about before. That means it looks like a nice bowl in parameter space, right? So it has a unique global minimum if we can only get to it. So kind of what this means is that, as long as I don't mess up the step size on gradient descent, that just kind of using natural, step sizes, eventually I will get down to the bottom of this bowl and I will get the unique best W according to this cost function, right? So even though this is a nonlinear cost function, which in theory could be a real mess to minimize, in practice, this is like a nicely well-behaved function. I think I mentioned that, we like these convex functions because it means that the unique global minimum exists. I'm not proving that it's convex in this class, but I'm just letting you take it on faith, okay? And so, the cost or the gradient for the multiclass case is similar, right? So in the multiclass case, basically, I'm just doing this for each of the WJs that I have. So the gradients are similarly easy to derive. And so the last thing I'll say about this, I guess, is that there are better ways of doing optimization than gradient descent. So just in passing, what I'd like to say is that we can do even better, by which I mean faster convergence of this iterative algorithm by minimizing this cost function using a different algorithm, right? So we can use a different algorithm using what's called a second order optimization algorithm. What this means is that, not just, the first derivative, like the gradient, but also second derivatives. And so I'm not going to, I'll write down a couple of equations here. One thing I will say is that, learning more about this would require you to take a class like numerical optimization in the math department, right? Which is, I think, a good class to take if you're interested in machine learning in general, right? But just like, so kind of in a very high-level, sketchy way, right? The idea behind a second order thing is that instead of just fitting like kind of a tangent line to the function and going down the tangent line, instead I fit like a bowl shape to where I am in the function and try to find the bottom of that bowl, right? So to make that bowl, what I need is the matrix of second derivatives. I need this kind of matrix of second derivatives where I take the partial derivative with respect to each of the parameters. This is basically called the Hessian, the m by m matrix of second partial derivatives. If you ever did, I'm trying to think of where the Hessian might have come up in calculus. Like if you took vector calculus, I feel like you might have seen this quantity, right? Like if you ever did things like div and curl and so on, like this is kind of like a vector calculus quantity. And the idea is that this is a matrix, and I can design an algorithm that's kind of similar to gradient descent, where I update my W using this Hessian times the gradient. So this is an algorithm that uses both the gradient and the Hessian, right? And so instead of just taking a multiple of the gradient, which is what I would do with gradient descent, I actually multiply this gradient by this whole m by m matrix, right? This is called the Newton-Raphson algorithm. And again, you can read more about this. Again, just like the gradient was not that hard to compute, the Hessian is also not that hard to compute for this problem. You can write it down very easily in terms of the x's and the y's. There are kind of trade-offs in the sense that, I have to, at every step of the way, I have to invert this matrix, which takes some time because matrix inversion is, like an n-cubed operation, right? But on the other hand, the idea is that I would need to take a lot fewer steps down these, iterations to get to the answer, right? So it's kind of a trade-off of doing more computation at every step versus needing fewer steps overall. And so again, if you are a optimization person, then that's the trade-off that you may want to make. And again, when you are applying a logistic regression algorithm in MATLAB or in Python, you don't have to think about any of this stuff, right? So like it will choose step sizes, it will decide whether it's going to use the Hessian or not, right? That's not usually the level of down in the weeds that you as a user have to be worried about too much. But I think it is useful to understand, like, how do these optimization problems work? And are they easy or are they hard, right? So let me just write down, just so I have it on paper, a little bit of what I tried to say, which is that, considerations, this H is easy to write down. It turns out it equals this sum, just if you want to know it for, you're not going to need this for the exam or anything, but I can just tell you what the sum is, right? So like all these things are easy to compute, right? It almost kind of looks like a covariance matrix kind of thing. But we need to invert it at every step, which, depending on how many parameters I have, could be relatively costly. But trade-off is that generally fewer iterations are needed. right? So I may get to the answer in like 2 or 3 of these Newton-Raphson steps as opposed to like 19 or 20 gradient descent steps. And so this is also just in general, if you're a signal processor, you may see the term iteratively reweighted least squares is another name for this kind of idea. And again, this is I think going a little bit farther beyond what we need to know about, but just kind of like as a machine learning person, you may come across these terms, and I just want to say them once so you can have a vague memory that, oh yeah, he said something like that once back in the day, right? Okay, so that's the basic idea. And, honestly, at the end of the day, it's like, okay, well, this is all great, but at the end of the day, we're still just like splitting the world in half with a straight line, right? So if I go back to my, my example, like this is the example I showed last time with linear regression. Let me kind of why am I here? Get rid of this still here. I don't know why my window is not all the way down. Get down there. Right. So this is kind of like what we were talking about last time. This is Fisher's discriminant applied to these data sets, right? If I apply logistic regression to the same data, and again, here I'm just using a MATLAB package, I get, a different pair of lines that separate the data, right? And it's like, okay, well, why are these lines any better than those other lines, right? Well, one reason these lines are better is that they are a little bit more principled, right? So now I can kind of understand that each of these guys, if I were to query it, unfortunately I can't do that in this interface, but I could now kind of like click on each of these data points and I could get a vector that would give me a 3-vector of basically interpretations of probabilities this vector, or probabilities this point is in each of these classes, right? That gives you a nice kind of probabilistic interpretation of the data in a way that you don't get from Fisher's discriminant, for example, right? But the lines themselves are still just straight lines. Now, in the same way, we could use logistic regression to find nonlinear decision boundaries by putting another nonlinearity in the mix, right? So, for example, I could, go back all the way to here, right? This is like the very beginning lecture, or very beginning slide, right? So I could go all the way back and say, okay, well, this x here doesn't need to be the raw features. It could be like some phi function of the feature, phi function of the input, right? So instead of just looking at the raw input vectors themselves, I could say I'm going to take some function of these, extract some features from my inputs. That phi function could be nonlinear, and then I'm going to use this other nonlinear on top of it, right? So that would allow logistic regression to generate decision boundaries that were not straight lines at all in the original space, right? And again, if you look at the book in particular, the classification section in Bishop, it seems like almost all those examples are using using logistic regression with both straight lines and also different examples of, well, what if we used a nonlinear function? We could see that it's a straight line in the space of that function, but in the space of the original features, it's some weird sort of decision boundary, right? So again, you can take a look at the figures in Bishop to give you some idea about all the funky things you can do by introducing some further nonlinear features. Okay, let me stop and ask. Questions or comments? It was a very mathy lecture, I know. Okay, so, and like I said, when I ask you to do this on the homework, we will again provide a Python notebook that has hints for what is the logistic regression function that you should use, right? I provide in the homework which ones I know about in MATLAB, but I'm not quite sure what the Python notebook will look like. The point is I'm not asking you to implement all this stuff yourself. I'm asking you to apply it and understand it, right? I will ask you to implement Fisher's discriminant on your own because I think that's a very easy thing to do. But the other one, I think that you can just use packages. So, and then again, just kind of like a foreshadowing is that on Monday we will talk about support vector machines, which is yet another way of drawing a straight line connecting or splitting up the points with, again, a different interpretation about what is the best straight line that I should draw, right? It's just like a different cost function, and we get a different decision boundary. So that's what we're going to do on Monday. Okay. Any final questions or comments? Yes?
With the H there, how do you get that one again?
how did I derive this? I didn't actually do it in class. I mean, I basically am taking the cost function, I'm taking the derivatives with respect to, I'm taking the two partial derivatives, like this mixed partial derivative, right? So this is the definition of H, called the Hessian, which I should just write this down, the Hessian. And then it turns out that the Hessian in this problem turns out to be this function, right? But I'm not going to derive that. It wouldn't be hard to do, but there it is. Okay, so